So now I'd like to introduce today's speaker, Michael McGehee. Michael McGehee is a professor of material science and engineering at Stanford University and the co-director of our Energy Innovation and Emerging Technology Certificate, which is offered through the Stanford Center for Professional Development. His primary research interests are developing new materials for smart windows and solar cells. He's taught courses on nanotechnology, organic semiconductors, solar cells, and polymer science. He received his undergraduate degree in physics from Princeton University, and his PhD was in material science from the University of California at Santa Barbara. There, he did research on polymer lasers in the lab of Nobel laureate Alan Heeger. Michael has strong industry connections, acting as a technical advisor to Next Energy, Plant PV, and Synovia, and from his teaching and mentorship, there's an impressive crowd of alumni from his lab. Many are now working in Silicon Valley startups, 9 of which co-founded their own companies, and 4 receiving the Forbes 30 Under 30 award. I'd now like to turn the floor over to Michael.
Hello, everyone. Thank you for participating in this webinar. I'm going to bring you up to speed on some exciting developments with Perovskite Semiconductors and their use in solar cells. But to get started, let me just say a couple things about the solar industry in general. In this graph here, if you look at the orange curve, you can see that back during the oil crisis in the 70s, solar panels cost about $100 per watt of power that they could generate in peak sunlight. And then that dropped rapidly and then stagnated during the 90s when there wasn't a whole lot of interest in solar energy. And then in the last 5 or 6 years, the price has dived down again, and now it's at about 50 or 60 cents per watt. And with that price reduction, if you look at the blue curve, you can see the installations rapidly rising with time, and now about 65,000 megawatts are being installed per year, and that's about the equivalent of 65 coal-fired power plants. So this is very, very exciting, and even more broadly, I would say that in the last year or two, we've reached a tipping point on addressing climate change, and a lot of people are getting on board, ranging from politicians to the utility companies, and I think there's a commitment now, and that renewable energy is likely to do very well. So solar still needs to get a little bit better. If the overall cost of an installed system was about $1 per watt, then solar electricity would be about the same cost as electricity from a gas-fired power plant. And here I've only shown you the price for the panel. Now installing the panel is even more expensive, and at a utility scale that could be maybe $1.50 per watt. And if you did it on a house, it might be something like $3.50 per watt. Now today I'm going to be focusing more on the solar cells themselves. That's what I do. And when you look at that data, you realize that with those expensive installation costs, what people who make panels need to do is raise the efficiency, because then you can get the power you need with a lower number of panels. And you can calculate how valuable it is to make a panel more efficient. And if you run those numbers, you find that you should be willing to pay an extra 3 cents per watt for an efficiency point. So in other words, if you could get a 20% efficient panel instead of 19, you should be willing to pay 53 cents per watt for it instead of 50 cents per watt. And indeed, if you look at the market, there's a range of products where the efficiency goes from 15% efficiency up to about 21, and indeed, those are the variations in the price. In some cases, people are willing to pay even more. For example, in the neighborhood where I live in Menlo Park, California, a lot of people have to pay up to 40 cents per watt, 40 cents per kilowatt hour for their electricity, because we have a tiered system, and the more power you use, the higher rate you have to pay. And a lot of people are switching to electric vehicles, and that's raising their electricity needs. And so they might want to install 6 or 7 kilowatts of panels on their roof, but they also don't have very large roofs, and a lot of their roof is not useful because they have chimneys and vents, and some of the roof might be shaded, and some of the roofs have complex shapes, and so they simply can't get the capacity that they would like when the panels only have 15 or 16% efficiency. And so it can make sense for them to really pay a premium to get higher efficiency panels. And so I think there's a strong drive for that. And here on the next slide, we can see how the efficiency has evolved over time for some of the most important technologies. Let's start with that black curve, because that's silicon. And right now, about 90, maybe 92% of the market is crystalline silicon solar cells. And the world record efficiency is 25%, but that's for a small cell, and that's for expensive things were done to make it. The panels would be more at maybe 15 to 21%. But the other thing I want you to see from that curve is there has hardly been any progress in raising that efficiency since the late 90s. So that efficiency is pretty much stagnant. Above it, that's the green curve, that's gallium arsenide, and you can go up to 28% with that, but it's a very expensive technology. Right now, it's about 40 times more expensive than silicon, and I don't see a pathway for a dramatic cost reduction there. If you look at the pink and blue, those are so-called thin film technologies, copper, indium, gallium selenide, and cadmium telluride. And the idea there is to use a smaller amount of semiconductor to try to reduce cost. And you can see the efficiency evolved over time, and now both of them are at 22%. But the news of today is that red curve, the perovskite. It just came out of nowhere around 2012, and the efficiency has soared up to 22, catching up with SIGs and cadmium telluride. And never in history has a semiconductor advanced so quickly for solar cell applications. And I think there are two reasons for that. One, there are some very beneficial properties that I'm getting ready to tell you about, and the other is that there's a community of solar cell researchers who've learned a lot over the years, and these people really know how to take a new material and make a good solar cell with it, so things move faster now. Maybe there's some of you out there who don't have an engineering background, so let me just say a little bit about semiconductors. These are materials that have a bunch of continuous energy levels that are filled with electrons that make up what we call the valence band. And then on the energy diagram, there are a lot of energies where there are no states that electrons can go into. And then there's a mostly empty band called the conduction band. And in between that is something called the energy band gap. And I will refer to that number a lot in this webinar. When light comes in, we can excite an electron from the valence band up to the conduction band, and it'll fall to the bottom of that band if we excite it up high into the band. And until that electron falls back down in a process we call recombination, that energy is stored. And what we want to do is get the electron to go to one side of the semiconductor and get the hole or the positive charge to go to the other side. And we want to extract that power as electricity. That's basically how a solar cell works. And the band gap is really important because if we have a large band gap, then most of the photons in the solar spectrum don't have enough energy to get the electron up into the conduction band, and so we can't absorb those photons. On the other hand, if we pick a small band gap, then the photons excite the carriers high up into the band, and then they fall to the bottom of the band in a process we call thermalization, and we lose all that energy. And so with a low band gap, we get a low voltage. With a high band gap, we get a high voltage, but we get a low current because we get one charge carrier per photon absorbed. And so on the curve of efficiency versus band gap, you see that it starts low, rises to a peak, and then it falls. And from this, we see that the ideal band gap is about 1.4 electron volts. And with one semiconductor, the highest efficiency you can get with the sun is about 31%. Now there is a trick, there's several tricks for beating that limit, but I'm going to focus on what I think is the most important one. We can make tandems, or other people call them multi-junction solar cells, and the idea is to put a large bandgap solar cell on top of a small bandgap solar cell. When you do that, the high energy photons are absorbed in the large bandgap cell, and because it has a large bandgap, we can generate a higher voltage, so we can capture more of the energy from those photons. And then the lower energy photons, they will go through, and we'll use a second cell with the smaller bandgap to harvest those too. So we can do better that way, and theoretically we can do up to 42%. But practically, for one junction, silicon is limited to about 25, and I think practically 35% might be about the best we can do with cost-effective means. But 35 is, considerably more efficient than 25, and so I think it's an attractive goal. This plot here just shows the efficiency you can get as a function of the band gaps. On the y-axis, that's the band gap of the low band gap cell. The x-axis is the high. You can see there that 42 is possible, and it tells us that for this application, the band gaps we want are about 1.1 electron volts and 1.8. So some numbers to keep in mind as I go forward. For single junction, we want 1.4 eV, and for two junctions, we want 1.1 and 1.8. Okay, now let me tell you about the perovskites themselves. Perovskites are essentially a salt, and you can dissolve them in a polar solvent. And when you do, you really don't have perovskite in your vial of solution. You have ions in there. And but then when you cast it or print it and form a thin film, the solvent will evaporate away. And as it does, the salt will form, and it'll be solid. And you'll get a crystal structure like you can see on the right side of the slide. The word perovskite, what it really means is just that crystal structure. It means the atoms are arranged in that way. But a specific example of perovskites that makes a good solar cell is methyl ammonium lead iodide. But there are other options. And on the next slide, you'll see on the top, as we go from the left to the right, we're gradually reducing the amount of iodine and adding in bromine, and you can see that the color is changing, and that's because the band gap is increasing from 1.6 electron volts to 2.3 electron volts. The visible spectrum is from about 2 EV up to 3 EV, so when the band gap is 1.6, the semiconductor can absorb all of the visible photons, and that makes the film look black. But as we go to the right, we get to where the film cannot absorb the red, and then it can absorb the yellow, and that's why the film starts to be colored. If you look at the bottom, we've replaced the methyl ammonium with another organic cation called formamidinium, and you see that that can drop the band gap from 1.6 down to 1.48. Later in the talk, I'll show you that we can replace lead with tin. And so by changing all of the elements in the formula ABX3, we have a variety of knobs for adjusting the band gap for whatever application. And by the way, if you use chlorine, you can raise the band gap all the way up to 3 eV, and you can also make red, green, and blue LEDs, but that would be a topic for another day. On this slide, you can see the cross-section of a typical perovskite solar cell. On the left was the original composition that a few labs like Namgu Park, Tom Miyasaka, and Henry Snaith, and Michael Gratzel discovered. And it evolved from the dye-sensitized solar cell. It has a film of titanium nanoparticles filled in with the perovskite and then sandwiched between a gold electrode and a transparent fluorine-doped tin oxide electrode. But pretty quickly, Henry Snaith realized that you don't actually need the titanium nanoparticles, and you can use the planar structure on the right, where it's just an uninterrupted film of perovskite. On the bottom is an energy diagram, and one of the key design rules is shown there. On the left is titania, and that's an example of what we call an electron transport material, and it needs to have its conduction band, which is that top energy level, being lower than the conduction band of the perovskite. That way electrons can go over there. But holes, which go upward on an energy diagram, they can't go in, and that way electrons can only escape to the left. In contrast, on the right side, we have a material just generically called the hole transport material. It can accept holes, but it cannot accept electrons. So these materials, sometimes we call them selective or carrier selective contacts, and they provide the mechanism to have electrons go out on one side and holes on the other. Perovskites have many wonderful properties. We've seen they have a tunable band gap. They're very highly absorbing. They absorb as well as any semiconductor out there. They, if you illuminate them with pulses of light, you can see that the charge carriers live for a long time. That means there's very slow recombination, which is one of the most desirable properties for a solar cell. A lot of semiconductors have defects at their surfaces, and charge carriers will recombine there, but that is very slow in the perovskite. For a lot of semiconductors, if you have a thin film with lots of small crystals, there will be recombination at the boundaries between crystals, but that seems to be very slow with perovskites. And it's all of those properties that make it possible to get as high as 22% efficiency. And moreover, we can print these things even on plastic, and so we can make a flexible solar cell at low temperature. And that's the property that cadmium telluride and CIGS don't have. So that's the good news. A balanced webinar has to present some of the bad news as well. These materials are very sensitive to water. A lot of you probably know that salts take up water, and these perovskites are no exception. But that just really means that the panels need to be packaged well. And it means that you need to cover the perovskite with an electrode promptly in the factory. You wouldn't want to have perovskite films sitting around, especially if the factory were in a humid environment. So you need to get it packaged promptly. Another one, it turns out the halogens, that's the iodine or the bromine, they move around very easily, and they can react with metal, especially silver. But I'll show you in a slide or two how to avoid that problem. And finally, methyl ammonium can leave the film relatively easy. It'll slowly come out at 80 degrees, and by the time you're at 100, 110 degrees, it will come out very quickly. And that could be a problem for field use where the temperature might hit 80 degrees C, but it's also a problem in manufacturing where sometimes you might have a processing step at, say, 130 degrees. My group has figured out how to mitigate some of these problems. We wanted to put a transparent indium tin oxide electrode on top. That's the material that's used in your flat panel display in your laptop. We wanted to sputter it, but it turned out that process would damage the perovskite, so we needed to put down a buffer layer. And for that, we used aluminum-doped zinc oxide nanoparticles. We could deposit those from solution in a way that did not damage the perovskite. And then we could sputter on that. These are inorganic nanoparticles. They're a little more robust, and they would protect the perovskite. And when we did that, we would put these solar cells on a hot plate in air at 100 degrees. And if you look at the picture here, you'll see the square in the center. That's where the ITO is. And there, the perovskite maintained its color. But outside of that, where there was no indium tin oxide, we found the material very quickly converted to lead iodide as the methyl ammonium left the film. So this demonstrated that the ITO would hold the methyl ammonium in, and moreover, we found that iodine doesn't seem to react with the indium tin oxide, and so we could run this solar cell in air with no packaging for a week on a hot plate at 100 degrees under one sun illumination. So this was a very big breakthrough, switching away from metals to using the indium tin oxide electrode. But that's only one of the things you can do. Before I give the next, let me just also point out some other research groups have found you can also use carbon paste as an electrode, again showing that the key to stability seems to be getting away from metal. And the second paper explains in detail why gold is problematic. It actually diffuses into the perovskite. So the second thing we do to keep methyl ammonium from escaping is to simply not use methyl ammonium. And if you use mixtures of cesium and formamidinium, you get a compound that we find to be stable at 150 degrees Celsius. Cesium is a little bit too small to properly fit into the perovskite lattice. Formamidinium is a little bit too large, but mixtures of the two seem to make a very robust perovskite crystal structure. And then the third really important strategy is simply to properly package these solar cells. And we talked a lot to the team at DuPont here in Silicon Valley who makes a lot of these packaging materials. And then we went to a company called D2 Solar that packages solar cells and makes panels for other solar cell startups that don't have all of that equipment. And here you put a rubber edge seal that you can see in black around the edge, and then in the interior you have encapsulation made of things like ethylene vinyl acetate or an ionomer called Serlin, and then you pull vacuum to get any air out, and you heat it to about 130 degrees and press on it, and forms a really nice package. And this is just industry standard packaging for solar cells. And then when you do this, you can put it through a torture test that the solar industry uses to predict if something is going to last outside for 25 years. They test for 1,000 hours at 85 degrees Celsius and 85% humidity, which is a really aggressive test. And we did that, and one of our 3 packages failed. It leaked and water got in, but 2 of them didn't, and we passed this test. After 1,000 hours, actually the efficiency increased. And so this is extremely encouraging that we passed that test. So the outlook on stability is that if you use the more stable perovskites, You use impermeable and unreactive electrodes and proper packaging. It looks like at least thermal stability can be obtained. We've also done a temperature cycling torture test where we go back and forth from 80 degrees C into a freezer at -40 to see if the shrinking and expansion will cause it to pop apart. And we passed that on the first time. And we're working on long-term tests under light, but those take a bit longer. And at least after 1,000 hours, things look encouraging, but it'll be a while before we'll have longer-term tests. So a year ago, I was a bit scared over the prospects of making these devices stable because they were only lasting for minutes. But huge progress has been made, and I think the outlook is positive now on stability. Now let me turn back to the tandem solar cell. So we know this concept works. The world record is 46%, and that's made with single crystal 3-5 semiconductors, basically the gallium arsenide family. I think that world record has 4 different band gaps in it. Unfortunately, those cells are absolutely tiny because they cost over $40,000 per meter squared to make. So I believe the future is a much, much cheaper tandem. And on the bottom, I think we could just use conventional semiconductors like silicon or copper indium gallium selenide, which both have the perfect 1.1 eV band gap. And then on the top, we need something that works even when it's not a single crystal, something that you would say is defect tolerant. And the perovskites have really emerged as an exciting candidate for that. There are a couple of ways that people could imagine making these tandems. There are actually probably far more than 2, but here, in my view, the 2 most promising. You could make a complete perovskite cell that has its own electrodes and mechanically stack it on top of, let's just say, a silicon cell that has its own electrodes. An advantage of that is that you can just use any silicon cell. You could get them from different companies, and they wouldn't have to modify their product at all, and you just package the perovskite cells on top. On the other hand, you can make a monolithic cell where the perovskite is directly deposited onto the silicon or SIG solar cell. If you do that, you have to match the current densities. If one of them puts out less current than the other, it will set the current for the stack. And that means you have to calculate and obtain exactly the right band gaps so that the 2 cells each get the right amount of current. And there's some engineering that has to be done to make the right interfaces between the 2. With the mechanically stacked tandem, you don't have to perfectly current match. On the next slide, I'll show you can still wire them up in series with each other. You can have a string of silicon in series with a string of perovskite cells, and you can just simply adjust the areas in order to get current matching. And if you do that, your panel will still only have 2 wires coming out of it. A few years ago, my group set out to demonstrate that all of this was possible, and the easier one to make is mechanically stacked tandem, and that's what we did. And back then, our perovskite only had 12.3% efficiency, and we put it on top of 17% efficient silicon, and we also had 17% efficient SIGs. And when you put those under the perovskite, the efficiency, of course, drops because a lot of the photons are absorbed in the top cell, but you could still get 5.7, and if you add those up, you get 18, which is better than either cell by itself. Since then, there have been a lot of advances, and I'll just have to skip straight to the world record, and this is from Christoph Balif's lab in Switzerland, and with a lot of things optimized, the efficiency is already at 25%. and I see a clear path to get this up to 30% efficiency. My group was also the first to demonstrate a two-terminal tandem in partnership with Tonio Buonassisi at MIT. They made a silicon cell with a tunnel junction on top, and then we put a perovskite cell on top of it. And here we got 13.7%, and we identified we were having a big problem with our whole transport layer absorbing photons, which we didn't want it to do. But a lot of progress has been made on that as well. Now the worldwide community has made many compositions of perovskites, and we have a lot to choose from. We don't have a great 1.0 EV band gap material, but we do have some pretty good ones with 1.6 electron volts. And in this next slide, you'll see with 17% cesium, 83% formidinium, and 17% bromine, 83% iodine, we've been able to make a two-terminal tandem with 23.6% efficiency. That was a validated world record by NREL about 10 days ago. And this is also, this is the same composition that passed those damp heat tests that I talked about earlier. So when we selected this composition, it was not only for efficiency, but we were also selecting it to be very stable. Finally, I want to tell you about something that's not published yet in a peer-reviewed journal. In collaboration with Henry Snaith's group from Oxford, we've figured out how to make a low band gap perovskite and make all perovskite tandems. This is on the Archives journal right now as the paper is going through peer review. And here we're adjusting the ratio of lead to tin in the compound. And if the tin composition is around 50%, we can get the band gap down to 1.2 electron volts. And that's not perfect for a two-terminal tandem, but it's getting very close to being the perfect band gap. And here you see the cross-sectional SCM of a two-terminal tandem. And right now, we're at about 17% efficiency. And we understand what some of the problems are. Our 1.2 EV material is far too thin. We just haven't figured out how to deposit a thick, high-quality film yet, but I think that will certainly be figured out. And we needed a 1.8 EV band gap to have proper current matching, but we also need a better composition for that band gap, and I see no fundamental reason why that can't be done. So I expect this efficiency to rise very quickly. We also made a four-terminal tandem with the low band gap material, and right now we're at about 20% efficiency. And it's very new material. We haven't been able to do full stability testing, but it was completely stable over 20 hours of testing under one sun. So I think the outlook for efficiency and stability is wonderful. You know, you've seen how the single junction efficiency rapidly rose to 22. I'd be very surprised if it's saturated there. I'm optimistic that single junction cells might go to 25, and that the tandems will go up over 30% efficiency. I know someone's going to ask me about the implications of lead being toxic, so let me address that before we turn it over to the Q&A. There's this paper in Nature Materials that's written by toxicologists who have no reason to be biased towards you know, perovskite solar cells, and they talk about, you know, what happens when people are exposed to lead. And you know, one thing that's very clear: the factories would have to be run in a proper way to protect the workers and make sure that they're not exposed to lead. And you know, there are plenty of industries that use lead and other toxic compounds, and it is possible to protect workers. And then when the panels expire and are decommissioned, it will be very important to take the panel apart and properly capture the lead. And then something else to think about, these panels are only going to have about 1 gram of lead in the perovskite layer. And just to put that into perspective, people may not realize this, but today panels already have 16 grams of lead that is in the lead solder. So it's a very small amount of lead. And moreover, if you took the panel and bashed on it for 5 minutes with a sledgehammer and threw it into a lake, well, then yes, the lead would escape. But short of doing things like that, it would be very hard for the lead to actually get out of a properly packaged module. There are 5 companies that I know of in the startup stage. Oxford PV is certainly the largest, and they're developing a 2-terminal tandem with perovskites on silicon. Full disclosure, I have co-founded Iris PV with Colin Bailey, and we're taking a different approach. We are mechanically stacking perovskites on silicon. Hunt Energy, led by Michael Irwin in Dallas, they're going with single junction perovskite, so they're going for an ultra low cost product. And Soleil in Poland seems to be doing flexible perovskite cells, and I don't know a lot about Weihua in China, but I have seen pictures of panels that are almost 2 feet across that they've already been able to print. If you want to learn more, we have a certificate program on energy innovations and emerging technologies. I teach a 3-hour module on solar cells. In that module, I say a whole lot more about the industry in general, and I go through all of the important solar cell technologies there, not just perovskites. And more broadly in the certificate, I think we cover all of the important topics on energy, so you can learn a whole lot there. These are all the people that, not all, but some of the people who helped do the research that I talked about from Stanford and some of our partners from outside Stanford, and certainly none of this would have been possible without them. With that, I thank you all for attending, and I will do my best to answer your questions.
Great. Thank you for that excellent presentation and for sharing some of the very latest research and collaborations. So now I'd like to hand back over to Mike so he can answer some of the questions that you've been sending through.
Okay, they've typed a lot of the questions for me. I can see them on the screen, and lots of good ones here. I'll start with are perovskites flexible or rigid? The films we're using are about a 1/2 micron thick, and actually pretty much everything is flexible when it is that thin. So what determines whether or not the solar cell is flexible is simply what substrate it is deposited on. And because our processing is at low temperature, we can build the solar cell on plastic, which is flexible. And there are indeed demonstrations in the literature of flexible solar cells. I will say for applications, though, the plastic will need to keep the water out for the lifetime of the product. And right now, we don't have inexpensive, flexible packages that provide a suitable barrier. So it's going to be important for there to be breakthroughs on that. But if the product didn't need to have a long lifetime, then it would certainly be possible right now to do flexible perovskite solar cells. Another question, would it be possible to go to 100% tin for the purpose of getting the lead out? And people are working hard on that, and I'm not sure what the latest efficiency is there. I'm sure people have gotten 8%, and I think it's in that maybe 8 to 10, perhaps as high as 12% with all tin. So it's not quite yet as good as lead. However, there have been reports that tin is actually more toxic than lead. The toxicity of lead is very well known, but it actually, as far as toxic things go, lead is not that bad, and there are a lot of things that are worse that just somehow haven't picked up the reputation. So I'm not sure switching to tin for the purpose of reducing toxicity is going to be helpful. People are also switching to bismuth, which unfortunately doesn't have the right charge, or it's not a +2, it's a +3, and then you have to balance that with a +1. So if you use silver and bismuth, for example, Hema Karunadasa at Stanford does that, but it's not yet anywhere near as good as these lead compounds. So suffice it to say, there are research groups trying to find lead-free compounds. Looking at some of the other questions, people are asking, what would the cost of these panels be? That's a great question. So we have worked with Mike Woodhouse at the National Renewable Energy Lab, who leads a team that does cost modeling, and they call companies and they find out what all the materials are going to cost, and they find out how much it would cost to use the tools to do all of the processing steps. And people in industry seem to agree that the results from that group are pretty accurate. And so they project that if you just did single junction perovskite panels, they'd be just a little bit cheaper than cadmium telluride because you can deposit the perovskite more easily, but not dramatically cheaper, and that's because so much of the cost is in things like the packaging and the junction box where the wires come out. So that's why, like, when people tell you they're going to drop the cost by an order of magnitude using solution processing, they usually have not accounted for the packaging. In the tandems, the way we like to think of it is, let's say you have a silicon panel and you want to upgrade to a tandem. We project that down the road the silicon panel would be about $80 per meter squared. We think the upgrade cost is going to be about $24 per meter squared. When you convert it to $1 per watt, we think that it'll be about the same, so it'll cost more, but it'll also be more efficient. Where you really win is that with these panels that have over 25% efficiency, you won't need to install as many of them to get a given amount of power, and the big savings will be over on the installation side of things, and that's why it's compelling to do this. Okay, let me look at some of these other ones. Someone's asking, what about the performance in direct versus diffuse light? So these will work fine in diffuse light. Unlike gallium arsenide cells, those are tiny and they are used with concentrators, and those are either lenses or reflectors that focus the light onto the cell, and they only work with the direct light. The diffuse light doesn't properly get through the optical system. But we won't be using concentration, and so ours will work fine. There's a fine point here with the tandems. Clouds change the spectrum, and so if you've designed your tandem to work well under the so-called AM 1.5 conditions, which is a bright day with no clouds, the tandem might not work properly with clouds, and nor will it work well at sunrise or sunset when the spectrum has changed. It will still work, and my group and several others are trying to calculate the loss over a typical year, and it appears that it could be around 10 to 15%. It's why I prefer the mechanically stacked tandem, because we can use a little circuit in between the perovskite and silicon solar cells to maintain the current matching condition, and so we wouldn't have to pay that penalty there. someone says, is there any work in progress to utilize graphene as a substrate? Well, graphene is also a pretty good transparent conductor, and there are some academic groups trying to use it as an electrode, and it would also, I think, dramatically improve the stability of the solar cell. Hardly anything can go through graphene. I hope there are advances in depositing large sheets of graphene. I haven't followed the latest on that, but I'm not aware of any real practical way to put down large sheets of it. I think you could have lots of small flakes, and that's kind of like those carbon pastes that I briefly alluded to that have been used, and they did result in very stable devices. Someone's asking about printing, and I think this is just being touched on, and at this time I don't think it's clear whether it should be slot die coated or blade coated or gravure coated or perhaps even inkjet printed with an array of nozzles. I think what is for sure is that it should not be spin coated at industry scale, because spin coating doesn't work well for very large area, and it also wastes so much of the solution. So we definitely want a printing technique where almost all of the ink does actually end up in the solar cell. And only a few labs are working on the scale up right now to go to larger area. There definitely needs to be a lot more work in that area. There's a question, do I think mechanical versus monolithic will be the better design for tandems? So I believe in mechanical, and I have a few reasons for that. One of them is I was saying how if the spectrum changes, during the course of the day or through the seasons, and the current match is lost, you could use circuitry to fix it. Another one is it's just a practical business concern. If someone were to make the high band gap top cells, they could partner with any company that makes either silicon or SIGs, and those companies would not have to modify their product. They wouldn't have to change the texturing that they use at the top of their cell. They wouldn't have to change their electrode pattern. Whereas if you go monolithic, you've got to keep the top of your silicon smooth, and that's not as easy as it may sound. Now, some believe in monolithic. When you do that, you get rid of one of the transparent conductors that you need in the mechanically stacked tandems, and each one of those conductors costs you about 10% of the photons. And so I'm sure eventually the world record efficiency will come from a monolithic design, but what's best to get a world record in an academic lab and what's most practical for business, I think, are two different things. So not surprisingly, people have asked for the expected time to market. It's always the toughest question for a professor to answer. I've certainly never seen anything progress as rapidly as this has, and a lot of times the community poses a problem and it gets solved in just a matter of 3 to 12 months. So things are moving forward very, very rapidly. However, I'm anticipating very serious financing problems. All of the startups are having tremendous difficulty raising capital. A lot of investors lost money, a total of billions of dollars were lost between 2005 and 2015, and so there's a reluctance right now to invest. And I guess if I look forward here, either some people are going to step up soon and invest, or the numbers are just going to get more and more compelling. The efficiencies are going to keep rising. The industry standard stability tests, I believe, will be passed. We may see academics and national labs start the scale up and demonstrate that there are no issues. And then hopefully investors will be willing to put in the tens of millions that will be needed for a pilot line. And then I think things could proceed very quickly. I think one thing some people learned from the failures of the last decade is that you don't want to have 8 to 10 innovations at the same time. You don't want to completely redesign the panel. You don't want to get into a situation where you need to build custom tools because you're doing something that's never been done before. And these designs that I talked about today, they can all be implemented with off-the-shelf tools that you can get from companies like Applied Materials. And you can even, like in Silicon Valley, you know, the tools are around, and you could be using used tools in a pilot line situation. And so in a best case scenario, I think products could be ready in a few years, but financing problems might extend that.
Okay. Well, thank you for answering those questions, and thank you for those of you who sent them in. We had a fantastic number. I think we've all learned a lot more today. I want to thank you for attending the webinar and hope that you'll be able to join us again in the future for other faculty talks. So enjoy the rest of your day.